Hi everyone, welcome to today's video. In today's video, we'll be going over recurrent neural networks, doing the forward pass and backward passes from scratch. I will be showing the intuition behind them, the math behind them, and then finally the code behind them. So yeah, let's hop into it. So, what is a recurrent neural network? So, an RNN is a type of neural network with recurrence, which gives it the ability to remember or hold memory of things in the past. Um, this makes it really useful for working with things in sequential order, such as time series, forecast data, and even things like sentences, because obviously in a sentence, the order of the words matter. This is why RNNs were used previously for a lot of tasks within machine translation, or as I mentioned earlier, weather forecasting. And this was all possible because of a small part in the hidden layers called the hidden state. The hidden state is basically the way in which the RNN remembers the previous data at previous time steps. So let's get into the actual architecture. So first here we have the input layer. At the input layer, we take the input at time t and we basically multiply it by some input weights. Um, this then gets passed onto the hidden layer, and at the hidden layer, there's two things that go on. One, if we are time step t, where there exists a time step t minus 1, we multiply that hidden state, the previous hidden state, by the hidden weights. Um, if not, we don't do anything because, for example, here, there's no previous hidden state, so you actually cannot do anything. But once you do that multiplication, then you want to add that to the previous input, which is multiplied by the input weights, and then add a hidden bias to it. So let's go into this overview here, which is a little more complex, but I'll walk you guys through it. In the previous architecture diagram that we saw, we had input layer, which was the input at time t for a sequence. So we have that same here. We have the input x, which is that input from the sequence, and we have some weights here, which are multiplied with the input to give us this value xi. So then as we move through the network, um, then we get to the hidden layer portion. At the hidden layer, there's two things that can happen. One, if there's a hidden state already initialized, we would multiply that hidden state by the hidden weights, and here we would take the nonlinear activation function, in this case it's the hyperbolic tangent, and we add the result of xi to xh of t, and we add a bias. In the case that there isn't a previous hidden state, so for example, where time step t equals 0, then we would just add the uh, bias and the xi input. So after we calculate this hidden state, we then go here and calculate the output of that layer. So that's going to be y equals the hidden weights multiplied by the hidden state, or sorry, the output weights multiplied by the hidden state. And we're going to add the output bias, to which is going to come here. And we're just going to be able to plug this prediction into this formula. We're going to test against the actual correct prediction or the correct label, and then that's going to give us our loss. So actually, the forward pass is very intuitive because we're just doing some multiplication and addition as we move through time. So the other thing that's important of note here in the hidden state is that there's two things that happen once the calculations are done. One is that the hidden state now gets stored in order to get passed onto the next time step, because the hidden state at times t affects the hidden state at times t plus 1. The other thing is that the output gets passed to the output layer in order to do some calculations. And so I've listed here all the calculations that we did throughout the forward pass. And the reason that these are important is because whenever we go through the backwards pass, or as we are calculating the gradient, um, we're going to need to keep track of all these. So now let's get into the backwards pass. If you're not familiar with what the backwards pass of a neural network is, in a backwards pass, we basically are looking to minimize the loss. And the way in which we minimize the loss is by tweaking our parameters, which in this case are our weights and our biases, in order to see how we can tweak them in order to minimize the loss, or basically have it go down to the lowest we can. And the way that this is done is called through gradient descent. And gradient descent, we basically compute the gradient of the loss and we do a lot more other calculations in order to figure out how we can get that loss to be the minimum as possible. And so in this diagram, what I did is that the forward pass is in white, as you can see, but the backwards pass will be in red because we're going backwards. The interesting thing about backwards pass in a recurrent neural network is that you're going backwards through time, right? What does it mean to go back through time? The reason I say that is because let's go back to what I said earlier, that the hidden state at t equals 1 affects the hidden state at t equals 2, right? So in this case, um, the output loss that we get is not just affected by the hidden state at the last time step, it's affected by the hidden state at all time steps. And so that's why backpropagation through time is the name of the backwards pass in a recurrent neural network. So in order to actually do backprop through time, we first have to calculate the partial derivative of the loss with respect to the loss. The partial derivative of, let's say, something with respect to itself is always 1. So we already have that pretty trivial calculation. The next thing to do here is calculate the partial derivative of the loss with respect to y. Why is this? The reason why is because the only thing that prevents us from going directly to the loss is this y value, right? And so the way in which we calculated the loss function was with this right here, this squared error. And if you are familiar with calculus, this is actually a pretty easy derivative to take because the only term here we have is y. And so when we take this derivative, we would get something like yi minus y, because we multiply this 2 and this cancels out, and then we multiply by the inside, which gives us yi minus y. Now, before I get into calculating all the other partial derivatives, I will explain why backwards propagation through time can be kind of complicated. The reason for this is because backpropagation is basically a chain rule. We're chain ruling all the way back to the inputs, because in order to figure out how these inputs influence the loss, we need to see their effect on the loss. But in order to properly see that, we must travel back in time and through our sequence or the network to see how each small change affected the effects of the inputs. So instead of looking at a diagram above, which looks kind of scary, I went ahead and wrote down here some of the formulas for how we can see how each parameter affects the loss. So for example, if we look at the input weights, Wx, um, the way in which we know how to upgrade them, or basically the way in which we perform gradient descent to minimize the loss, is that we take this negative epsilon, so epsilon is our learning rate, and we multiply it by the derivative of the loss with respect to um, the input weights. And so what this will do is that it will show us how much the input weights actually affect the loss. And so this actually is very complicated at first, because how would we know how these input weights affect this? Well, the way is actually, as I mentioned before, through a chain rule. So the first part is that in order to get to the input weights, we must go through an entire network. And so first, we'll have to find the partial derivative of the loss with respect to y. We already found that. So we can now move on to the next step, which would be finding the partial derivative of y with respect to the hidden state. The way in which we do this is we look at this formula right here, and we see that the hidden state actually does affect the output of y. So when we take this partial derivative with respect to h of t, we get just wy. That's actually a lot more trivial than you would expect it to be. If we were to keep going, we would have to calculate the partial derivative of h of t with respect to the partial derivative of a hyperbolic tangent. Now, this gets a little more complicated because if we look at this formula here, um, this is h of t, and this is all that goes into the hyperbolic tangent. So in order to take the partial of this with respect to tan of h, we'd actually have to do a little bit of a calculation here. The calculation that we must do here is just take the derivative of tangent, which is actually 1 minus tan h squared, and then we would have to go back here and look the partial derivative of hyperbolic tangent with respect to wx. And when we look here, we remember that x of I is equal to x times wx. So if we were to take the partial derivative of this with respect to wx, we would just get x of t, because this is the only variable which the wx affects. These are all constants, which would therefore go to 0. And so if we were to write it out here, and so after calculating all these, I've gone ahead and written it here in yellow. And we can see here that the partial derivative of the loss with respect to wx is actually not as complicated as it might seem. So we have obviously the input sequence at time t, and then we multiply this by the derivative of hyperbolic tangent times the weights and times the difference in y's. So if we were to do this for all these values, which I'll leave up here so you guys can do yourself, I think doing this by hand is actually really good practice and a really good way to get better at PPTT. Um, but if we were to do this for all these values, we realize that once we actually get the local gradient, getting to the gradients that we want to is a lot simpler than we expect. It just basically having to do a chain rule backwards. And the reason why x is not, or wx is not affected by the hidden state is because at no point do these weights ever affect the hidden state. But for example, with something like WH, which are the weights of the hidden state, then these derivatives here are actually reflective of the hidden state at a specific time step. So I'll leave you guys to do that by yourself. So I've gone ahead and put up all the results in the screen for you guys to, check your answers with. But basically, um, we can see that it's actually a lot simpler once you see the resulting gradients. So for example, let's take a look at the uh, partial derivative of the loss with respect to the hidden weight, or sorry, the output bias. We can see that it's just a difference in y's times 1. Where does the 1 come from? It comes from the partial derivative of y with respect to the partial derivative of the output bias. And if we take a look here, y is equal to ht times wy plus d, where this is the bias. And if we take the derivative of this with respect to d, it's going to be 1, right? And so this plays a lot of importance when actually calculating the gradients in code, because something like this we can calculate very easily since we already have access to this, and something like this, the partial of the output weights, we can also calculate very easily since we already have access to the hidden state from the forward pass. So now that we've walked through the math or the intuition of both the forward pass and the backwards pass, I want to go into my implementation of a RNN. I implemented in Python using PyTorch, and I tried to use as little help from libraries as I could. Um, I will show you guys how we did this. And so the first thing I did was just initialize all these weights. Um, I obviously take input dimensions, hidden dimensions, and output dimensions, which you can specify as you want. I actually kept this RNN pretty simple. For pokes and learning rate, we'll look into later. But basically, just initialized all these weights to random values at first. Um, I think this is the best way to do it. This is how it's been done by many other people. You can initialize it whatever you want, but it's just what I suggest. Then when it comes to the forward pass, it's very similar to the process that I mentioned earlier. You have hidden state and output states. You initialize these to 0, and you need to store these for backprop. But you initialize these to 0 because originally there is no hidden state. And that's something that we're going to see with this value here, previous hidden. It starts as none because at time step t equals 0, there's no hidden state. But anyway, what we're going to do here is we're going to go through each time step in the sequence. So what I'm using is a sequence of size 3. So we're going to go through 3 time steps. As I mentioned earlier, there's 3 layers. So there's an input, hidden layer, and output layer. Here, the input layer, we're doing what we mentioned earlier. We're calculating x of I by doing matrix multiplication of the input x times the input weights. At the hidden layer, if the previous hidden is none, then we're just going to take the hyperbolic tangent of x of I plus the hidden bias. Otherwise, if we do have a hidden state, then we're going to multiply the previous hidden state by the hidden weights, and then we're going to add it to our xi that we calculated earlier, and add it to our hidden bias. This will give us the hidden state for the next time step, so we're going to update previous hidden to be xh of t, which is actually the hidden state value. Then finally, we're going to calculate the output layer here, which again, as we remember, is a formula y equals h of t times wy plus the bias. In this case, h of t is our hidden state, and then we multiply it by the weights, and we add the bias. We're also going to store this for backpropagation. At the end, I'll just return these, just because I mentioned here we need them for gradient descent. So the backwards pass is actually a little more complicated in terms of the actual calculations, and you'll be able to see that here. But first, we want to initialize all the possible derivatives of the parameters. So I have for the input weights, the output weights, the hidden bias, and the output bias. These are all initialized to 0, and they're in the size of their respective parameters, just to make sure that the dimensions are properly kept track of. So the reason we need this hidden t, which is just a hidden state at the last possible time step, which in our case, since we're using 3 time steps, this will be at hidden of t equals 3, but to index properly you do -1, is because this is what directly affects our output. But however, in order to calculate the gradients of the previous hidden states, we do need the hidden state that followed those. But before we can actually calculate, we can do 3 easy derivatives out of the way. So as we saw earlier in the drawings, the partial derivative of the loss with respect to the output bias is actually just equal to dy times 1. Dy in this case is just yi minus y. We can also calculate the partial of the loss with respect to the output weights very easily by just taking the hidden state at time t times the difference in y. So we get these two out of the way really quickly. And then finally, we can also calculate the gradient of, the partial derivative of y with respect to the partial derivative of h of t by just taking the difference in y multiplied by the output weights. And we transpose in order to make the matrix multiplication work properly. So once we get to this step, it starts getting a little more tricky. We have to keep track of the next hidden gradient, because since we're traveling through time, we require on the one from the time after. So for example, at time step t equals 2, we require the hidden gradient from t equals 3. And that's what we're storing here. So for then, we're going to loop all the way backwards to time step t equals 0. And each time we're going to be unpacking the hidden value, or the hidden state value at that time t. Then we're going to calculate the derivative of hyperbolic tangent, which, as I mentioned earlier, was 1 minus tan h squared. That's what we have here. And then we're also going to multiply this hyperbolic tangent gradient by the next h grad, which is just the hidden gradient from the time step ahead of us. That will give us the partial derivative of h with respect to the partial derivative of tan h. As we can refer to in the earlier formulas that I showed you, the partial derivative of the loss with respect to the partial derivative of the hidden bias is actually just equal to h grad, which we already have. So we can just add this to this variable, and now we already have 3 out of the 5 possible input parameters gradients. Then we can move on to calculating the partial derivative of the loss with respect to the input weights, and that's actually very simple since we already have this h grad. This h grad is basically containing all the chain ruled values up to this point. If we refer back to that last screen I showed you with the formulas, the only thing that's missing is x of t, and sequence at time t is x of t. So we can just multiply this and add it to our derivatives. Finally, if t is greater than 0, meaning that we're not at the first time step, then we can take the previous hidden state, so hidden at t minus 1, and we can multiply that with the hgrad to add it to the partial derivative of the hidden weights. We only do this at greater than t equals 0 because if this was equal to 0, we'd go to a time that doesn't exist. So we're just checking for that. Finally, at the end, we have to update the next hgrad by multiplying the current hgrad by the hidden weights. And the reason we do this is because if we remember back to the diagram of the overview, um, at the hidden layer, there's two outputs, which are one that goes directly to the outputs tensor and one that goes directly to the hidden state tensor. And so we're basically multiplying by the weights in order to undo that multiplication that we did earlier. Then finally, we're just going to return all these derivatives. So once we have all these derivatives, what we can do is just multiply them by epsilon, which is our learning rate. This learning rate is stored within the class of the RNN, but you can change it to whatever you like. And you subtract these from the input weights. This is a pretty simple function, and it's just done like this for modularity. So finally, when we piece all of this together, we basically put together a function called train, in which we take the x and y values from the data that we're trying to predict. We take the validation x and y as well to verify the loss. And so we'll start this process here where we loop through the number of epochs that we're going to have. And at each epoch, we want to calculate the loss of that epoch. So first, we'll loop through all the possible inputs, which value x consists of time sequences, right? X of 0 is going to be a sequence of size 3. And so we'll call forward pass on this. If you remember, this forward pass will return us the hidden state and it will return us the outputs. The final output, or like the prediction, is at the last index because that's the final output of the network, right? So that's our y hat. Here we're calculating the squared error as we saw before, and here we can calculate dy, which is just difference between the actual prediction and the label, and we add it to the epoch loss. After this, we can call the backwards pass to compute the derivatives for all of our input parameters. And then once we obtain these parameters, we can call the gradient descent steps with the learning rate to actually update these parameters. We're also keeping track here of the validation loss in order to properly compare our train set accuracy to our validation set accuracy. And we're just going to print these out to see how it looks. So basically here I've created a script where I first take in the data from a CSV file. As I mentioned earlier, this is for temperature sequences. So I'll take time steps 3. I'll take the first 3 time steps, which are going to give 3 temperatures. And then the label is going to be the one that follows that. So at time equals 4. So that's basically what we're going to try to predict. And here just do an 80-20 split in order to actually properly see our training versus validation loss. And so here in this main function, I'm just calling the input preparation to get the actual x and y values that we're going to use, and I initialize the RNN. Here I also lay down some predictions of sequences. This is actually from the CSV file itself, because I want to see the prediction before training, which I don't want to spoil, but it's going to be really bad, and then the prediction after training. So we're going to run this train loop, and we'll see that for these sequences, we'll see what the network actually predicts. So here I'm going to run the script, and what we'll be able to see is going to be the training loss compared to validation loss at each epoch. You see it starts out relatively high, but as we descend, it actually starts decreasing. The leaps in how far it decreases are actually not as big as I would want, which means that I could potentially tweak the learning rate to see how it will play. But we're just going to let this run and just observe how the loss goes down as we train this network. This is basically showing that our network is properly learning, right? We want to make sure that the validation loss is actually steady to ensure that there is no overfitting. But so far, it seems to be working well. So we're just gonna let this run for a little bit longer. Yeah, and there you have it. At the end, we'll see that the input sequence was 0.22, 0.13, and 0.14, which are the temperatures in Celsius. And the prediction of our network was 0.19. The true value was 0.189, which shows that this is very close to the correct prediction. With the next sequence, it did not get us close. It was off by zero point 0.5, but or 0.05, sorry, which is not that bad. And then with the third one, it was off by a lot more. But this is definitely a harder sequence to predict than the first one because clearly um, there's some patterns that the network can pick up with or not. Thanks for watching. If you enjoyed, make sure to leave a like down below and subscribe. I just want to say a disclaimer that this is also one of my first times working with RNNs, and as you guys are learning, I'm also learning, and so there could have been some mistakes I made, and some things I might have done incorrectly. For example, I know I ran the model for 200 pokes. That's definitely way too much, but I just wanted to see what would happen if such, right? So again, if you enjoyed, leave a like down below, and I'll see you guys next time.